We start with a constant function, f of x equals 6. Since the function value never changes, the difference quotient will always lead us to 0. Now let's look at a linear function, like f of x equals 2 minus 3x. A linear function represents a constant rate of change, which is its slope. To find the derivative of quadratic functions, we use algebraic expansion. Let's start with 4x squared. First, we replace x with x plus h and square the binomial. Expanding that gives us 4x squared plus 8xh plus 4h squared. Now we subtract the original function. Notice that 4x squared cancels out perfectly. Dividing the remaining terms by h leaves us with 8x plus 4h. As h approaches 0, the term 4h vanishes. We are left with 8x. That's our derivative. In every derivative limit problem, you'll reach this stage. The core of the difference quotient involves this h in the denominator. This small variable, h, is our target. It is the key to solving the limit. Here is your golden rule. In every single problem, that h in the denominator must disappear. If it's still there when you plug in 0, you have an algebraic error. Watch as we cancel the h. By factoring it out from the numerator, we clear the way to evaluate the limit. Always remember, the h must be canceled before you can let h approach 0. It's your most reliable self-check tool. When we see square roots in a derivative, we use the conjugate trick. We multiply the numerator and denominator by the conjugate of the radical expression to clear the roots. Multiplying by the conjugate creates a difference of squares in the numerator, which eliminates the square roots and reveals an h that we can cancel out. Now notice the numerator simplifies to just 2h. The h in the numerator and the denominator cancel perfectly. This is the goal of our algebraic manipulation. Finally, let h go to 0. We are left with 2 over 2 times the square root of 2x, which simplifies down to our final derivative. Today we tackle a classic hurdle in calculus, finding the derivative of a rational function like 9 over x using the limit definition. First, we substitute our function into the definition. We have 9 over x plus h minus 9 over x, all divided by h. This is where we find a common denominator for the numerator. This groups our terms into a single fraction, which is essential for our next step. Now notice how the 9x terms cancel out, leaving us with negative 9h in the numerator. This is exactly what we need. We cancel the h in the numerator and the denominator. The moment that pesky h is gone, the problem becomes much easier to solve. Finally, we let h approach 0, and we are left with negative 9 over x squared. Remember, watch your negative signs, and you will get it right every time. You might wonder why we grind through these limit definitions when AI can do it in a second. Think of this as going to the gym for your brain. If you skip the manual steps, advanced topics like the chain rule will feel like black magic. When you solve these by hand, you develop the pattern recognition needed to see how rates of change interact. The best way to study in 2026? Solve your derivation on paper first. Then use a tool like Desmos to plot the function. If your manual math matches the slope of the graph, you truly own that concept.